Video is rolling.
Well, everybody knows me and knows that I'm not Brad tonight. Brad had to call into work, so I'm filling in for him.
Hi, Brad.
We are going to talk about steam and what I've been taught by steam over the last 45 years. I know it sounds kind of boring, but you never know everything about steam, and you've never seen everything about steam. Steam behavior never changes, and steam can hurt you even if you're careful. That's not my arm, but my arm looked like that last February. Opened up a boiler that was supposedly drained, and it burnt, and I got burned. So, you gotta be careful. Expect the unexpected, never take anything for granted, test and verify everything. So, I cut my teeth on propulsion, and got a couple of videos that I scabbed off of YouTube.
Steam power plant for ship propulsion. Basically it consists of water tube boiler, steam turbine, condenser, boiler feed pump, gearbox, and propeller. Steam is generated in boiler from water and superheated. Superheated steam passes through steam turbine and thermal energy in steam is converted to rotational mechanical energy in steam turbine. High rotational speed is reduced to lower speed in gearbox to turn the propeller. Exhaust steam in turbine is condensed in steam condenser to water. Water is pumped back to water tube boiler by boiler feed pump.
So, to give you an idea what that turbine's doing, on the ship that I was on, we think it was around 10,000 RPM and reducing it down to 50 on the shaft through the reduction gears. That's a pretty fast thing when we're clipping along.
Now that's all for what? Just to get your torque by reducing?
You know, that's a good question. We're running that turbine to get the speed up, so you're probably right. It's a two-stage reduction gear that, on the ship that I was on. See? The
Other question, what's the condensate cooling pump? Something I noticed in that.
let me go back to that.
Lower right-hand corner.
Well, you're taking seawater and you're helping condense what the steam was.
Do what? I can't hear you.
You're taking seawater on the cooling side of that, and you're dumping it through the condenser, which is bringing the steam back to condensate.
Oh, it's through heat exchanger. I see.
Yep.
Okay.
Yeah. It doesn't show up very well in that.
Yeah. Okay. I see what you're
Yeah.
doing.
And then,
Because it's obviously if it's superheated, you're.
So that steam's not just staying there at the ready for the turbine. The excess has to be condensed back down, so you're still moving and generating steam. Steam's flowing, right? It's not deadheading up against the turbine.
well, if we close the throttles, there's no steam going to the turbine at that point, so the boilers.
Then what? Then does it condense and go back to the boiler?
It's gonna condense what's in that line, yes, but the boilers are just gonna back down. So
Little throttle back, yeah.
modulate. Oh,
Because I was watching this movie Battleship,
yeah,
and I was just trying to figure out how that worked.
so this is a. So there's three levels of the fire on this ship. The center level that you're going back to right now, what they call the water check level, and the second cycle level of the boiler. You're going there and close the two-story or about a 10 by 10 console, called the pneumatic controls.
And Terry looks young in that picture.
The upper level we could have gone up that ladder, got the floors on it, and then the economizer for the boiler, lower level. The economizer will keep the steam up in the more heat stack, superheating. This is how we lit the boilers actually. This later did a couple of them.
There's a roast of marshmallows.
We didn't have the safety gear. This is 10 years after I got out. You can see the pressure gauge and temperature gauge on that console. They're running about 1,275 pounds of steam at about 1,000 degrees.
What kind of thickness was on the transfer components to get the steam out of the turbine? How thick is the wall thickness on pipe?
I've never seen it quite old.
For 1,200 pounds and 1,000 degrees. Probably pretty big.
So down here the manager fuel, there's 4 burners on each boiler. This is the alpha boiler, Bravo's behind me. Then your light up. You see Bravo's up the pressure.
Hey, the messenger over there?
We're up in attics, pump house, LA equipment. We're trying to ship, the last ship I was on, 10 years later.
The same ship? What was that?
Meyer Ford,
The what?
Meyer Ford,
Iron Ford?
1058.
I can tell you, my dad was on the Roosevelt as a boiler operator between World War II and Korea.
Really?
Yep. I told Perry.
That was CV still, right?
What's that?
Carrier designation was a CV, I think.
All I know is the name of president, look at Tommy's old papers, but he never spoke of it.
And I think that board had 12 boilers, if I remember correctly. That's the check.
It is a carrier, right?
So, you stand in front of that door and you have what they call a flare back, and when it comes out, it'll go right through you.
The rod?
The rod, the torch rod.
So was that whole compartment's full of gas? You're touching off, or what are you lighting there?
Naval distillate, which is like a light diesel fuel. Okay?
I didn't think it, so you carry that fuel oil, is that like a number 6 fuel oil or something?
Basically, the refined kerosene.
I worked with
basically.
that number 6 sulfur down there in
I
Maryland.
think it was like JP4, something like that. JP5 was jet fuel, so it was a step below that.
We had to clean them nozzles like every freaking day and then change them every 3 days. The nozzles, they get all gummy, you get the cleaners at the back of the boiler.
Kind of boilers.
They were Cleaver Brooks.
Okay.
Yep, 600 horsepower Cleaver Brooks and a little 250. Because I put a door on that bitch. We had to go up to Delaware and get a door because we had cleaners and burnt the shelf off the back. And they had a meltdown. And I guess you couldn't take something that wide down the highway without an escort. These boys, this is down in southern Maryland. So they had a drop deck trailer, put it on that, brought it down under the cover of darkness. And we rigged it down the boiler room to hang it on the back door pins. Yeah. That door, that
Just
boiler
so you
had
know,
no
we're recording
skin.
this, so you don't want to.
That's all right. Listen, I got sexually harassed because I went up there to look at this boiler and I was coming back and I get pulled over by a Delaware state trooper and she was a big girl. She was short and big. She comes up to the door. She says, license registration. I said, well, I gotta, it's in the glove box. Can I get out and go around and get it? She says, no, you can lean over. And I was like, right, this shit up. See, I almost felt so dirty. She reduced the ticket. I was like, thank you, officer. But anyhow, that boiler, when I inherited it, had no skin, all gone. Guy's like, yeah, you can pull the paper off insulation, put it on there. And we had sheet metal guys come in and painted it. Oh, yeah, that's 600 horse. I got an article on that. What they were doing was 125 pounds. Then he had a 40-pound process for cookers and bottles, and then they transferred to steam. But they condensed to a hogger, a condenser that was 3 stories high, to condense that 400 gallons per minute pump down to put a vacuum, put a 4-inch vacuum on the cookers so they could dry the product out at a lower temperature because it's in a vacuum with a jacket and not destroy the amino acid strands in the product. 1954 Buffalo back dryers, these vessels were. That was Bill Jack Pet Food. They still make their dry food and Marshall Ferret food today that way. They're the only ones that use steam for that.
Well, so, food processing is one that I forgot when I put this together, I'll have to add it. So, as you can tell, there's a lot of uses for steam. Propulsion, heating, sterilizing, process, power gen, cleaning, humidification, food processing, right? Steam's considered a gas. Steam can't be seen. You think of steam when we see actually water vapor coming out of a chimney someplace, right? That's condensing into a cloud. That's steam that's condensed already. Steam is normally seen as wet or saturated or dry and superheated. So, as we go on here, we're gonna talk about the saturated and the superheat. That's similar to what we see in refrigeration. And I put this in, again, never take anything for granted, test and verify. Primary discussion today is steam heating applications. Steam pressure can be ultra low, even into a vacuum, providing a wonderful heating mechanism. Look at our steam tables here, you have them in front of you. At 20 inches of mercury, we're boiling water at 161 degrees. You're coughing up 1,002 BTU of latent heat. Okay? 0 PSI, that isn't graduated where I needed it, but about a half a pound, we're still boiling at 212 degrees and we're coughing up 970 BTUs of latent heat. Right? Okay. At 5 pounds, what happens to our BTUs?
Goes down.
Goes down. Our boiling temperature is 227 degrees Fahrenheit, right? So let's go to the propulsion side. And I did this because that's the chart that I found. 1,285 pounds of pressure gauge at 650 is saturated. It's 1,261 BTUs of latent heat. We superheat it to 1,000 degrees. We're at 1,496 BTUs of latent heat. Have we really gained anything from going from 20 inches of mercury to here for heating purposes?
Not for heating, no.
We've lost it, right?
Right.
So what did we do? We spent a ton of fuel. Okay?
Are you talking about the efficiency of going from 20 inches to the 1285 PSI and you're only picking up 200 or 400 BTUs at max?
But how much did we put in?
Yeah.
Okay?
But unless it's a gravity system or a system that's gonna rise, right, with orbits and stuff, if you need to push on a lateral plane, you have to have the PSI for process,
Well,
for heating.
we're
no.
talking about heating.
For heating, no. Right.
Heating.
Yeah, no, you don't even have it.
So our ideal heating is like the old timers had it, sometimes, someplace in a vacuum, there's 0 pounds. Okay? We have, at that church, we have a vacuum pump. Don't know if it works yet. It'll be interesting to see what happens, right?
So those big old Kiwanis that have the vacuum system that draws all that air through, they shut off once the condensate's coming back. Once the steam's drawn back through the entire building, they shut off. Are those supposed to stay on to keep that whole system running in a vacuum all the time?
Typically, you're running about 8 inches of mercury.
Or do they have them that do just to clear the lines to get your steam out to the process
There's
fast?
so many different setups. I've built a couple of vacuum pumps myself out of CPVC. Fire department at University Heights still has one, it's been a long time. All it does is it sucks the air back through a water jet. We're using a monoflow T, pushing water out of the tube, back into the tube, and we're sucking the air with it. Okay? So, you're not ever gonna see hot water there, or steam, and you can't kill it like you can a vacuum. The concept there is, the boiler is way oversized for the building, after they disconnected half the building, and it seems to work. It's been like that for many years. So what, is there a downside to using low pressure? on a standard heating system.
Quieter.
There are downsides.
Yeah.
Well, you can't mask all your steam trap problems by blowing
Yeah.
steam back, but
Never hear of it, yeah.
if the system's right, then no, I wouldn't say there is at all.
Yeah.
And there's some chemical issues, you're not gonna get etching. Problem is, looking at flanges and stuff leaking, they start etching, the steam starts etching those flanges and stuff, it does more damage. You know, when you get a leak and it cuts it, what's the proper name for that?
Wire draw.
What is it?
Wire draw,
Wire draw?
yeah.
Yeah, so you don't need all that, you're just
No.
wearing stuff out. Pushing up against reliefs, doing all that, you don't need all that.
And what are we doing? We're burning fuel where we don't need to burn fuel, right?
True. And you know, when you go in these old schools and they're running 5 or 7 pounds, they're trying to push condensate back, that's it, there's no reason for that whatsoever.
They do that if you have zone valves, you have to have the pressure up, because if you open a zone valve on a low pressure system like that, it will suck the water right out of the boiler.
If you open a zone valve on a low pressure system being what pressure?
Sometime, somewhere around 0, 5 ounce, or half a pound.
Okay, you're saying because of the space.
Well, think about it.
If all the
How much
condensate
space, how much space does a pint of water take up?
I don't know, but the traps are supposed to close, so it shouldn't be air.
How much space does this take up when it becomes steam?
1,700 times bigger.
Sorry?
1,700 times bigger.
Yes.
The volume.
It's about 28 cubic feet of piping. Okay? So if you're happy and you got 28 cubic feet of piping open to the system, and you open another 28 cubic feet of piping, what's gonna happen? Poof. Steam travels at what, do you remember?
I don't remember that one.
Right around 90 miles an hour. I think it's 88 miles an hour.
There's not really enough in that system to travel like that.
Right, so if you build the pressure up, you have that buffer. So if you have heat exchangers.
Better have some slow open valves.
Heat exchangers, yeah, you should have slow opening anyway. Heat exchangers and zone valves, okay? You're still gonna have to run around 5 pounds in that case. So actually, I think we have that further on down. So, 1 pound of steam, what are we giving up in BTUs here?
What are we talking about now?
That's 0 pounds.
0 is 970 BTUs.
970 BTUs of latent heat, right? So we come to the trap, and it's gonna condense, and then we're gonna cough up a couple degrees of sensible heat at that time, and send it back to the boiler, hopefully, right? So steam wants to fill all the piping and radiation of the building, so it has to push the air out ahead of it. This is where the vacuum comes in. If you have a vacuum on that system, what's gonna happen? It's just gonna rocket through that system, right? Empire State Building's got a vacuum system on it, and they're running it less than 2 pounds.
It's not gonna like rocket through there unless, on a cold startup, it's not gonna rocket through there. These are just, the vacuum is to start the system up to pull that air out.
No.
Once the system's up and running, you're good.
Heating systems, they run a vacuum at 8 inches all the time.
Why?
Because they.
Once there's steam in there should not be any air in there. The vacuum should just be to remove the
what's our-
steam.
See the 20 inches of mercury there?
But water boils at 212 degrees at.
Yeah, but there ain't nobody around here smart to figure that shit out. Look at these churches and stuff, man.
Yeah.
Barely they can keep them running. There's nobody here running a boiler at 20 inches.
This
Where
is
is
This
this?
is why we're having this conversation.
Because I would be like, what?
Yep.
Yeah.
No. Can it happen? Yes.
Cleveland Gear had a vacuum system. And I don't even know if they're still around.
But it was designed as a vacuum system where it ran vacuum all the time. Wasn't
Yeah.
just for a startup
Right.
deal on a cold
Correct.
morning. It was that's how
Correct.
it worked. But why would you, okay, other than the heat, benefits,
Yeah,
there's really no reason to do that then, other than the heat benefits.
Energy factors, not getting as hot.
yeah.
You drop 40 degrees of water temperature, so you can actually save energy by doing
Well,
it.
it's all part of it, right? But if you have a vacuum on a system and you're closing zones off, what happens?
You're gonna build more pressure quicker too, though.
Yeah.
Close more zones up. The more zones you close, the less place you had to escape it to.
Right, so that's where, at Gear, they probably were running 5 to 7 pounds of pressure, because they were using it for heating and process. You with me?
I could see, you know, I've had 40 pounds of process, 60 pounds of process, and it was about the heat, and the 40 pounds was less, and, you know, so it was about the heat and what was engineered and needed, you know, so I can see that.
So in the vacuum pumps that we work with over the years, we set them at 8 inches of mercury, and they pull down to that and they shut off. Now, a lot of times those are trap systems, 2-pipe systems. Okay, that's where your air is coming out, your trap's all closed, what happens?
So you evacuate all the air and you'll get into your negative 8 inches as long as the traps are solid.
Traps are gonna close, right?
Yeah, suck it down.
All the
shut
traps
off.
are gonna close, now we're gonna go down to 8 inches and we're gonna shut off. One trap opens, what happens? That pressure starts to come up, vacuum pump starts again.
You said one trap does what?
If one trap opens, the pressure's gonna start coming up
It's real strong.
on a condensate return, right? So the pressure's gonna come up, it's gonna start that pump again. That's because you're higher.
What
than-
kind of traps are they using? Are they float? Are they F&T?
Yeah.
What type of traps? To
All-
have a positive process shut off,
All
yes.
kinds, all kinds.
I mean,
Yeah.
cause those are supposed to be flooded, those are supposed to be wet, so
All
they're not
kinds.
supposed to open until the float rises, or the thermostatic.
So you got bucket traps, you've got.
But is there a
F&T.
specific style trap
No.
used on a vacuum system, so when you walk in there, you're like, oh shit, that's a vacuum
No,
system?
No,
No.
no. Vapor systems have traps that are basically like a tube
traps.
right here, and it's got a plate in the middle of it. Okay, there is no solid shut off there. The water is, it's trapped. There's a hole above that water for venting. You don't see them all that frequently anymore, but they're out there. Okay?
Who's the steam experts other than Tom here in Cleveland? Who's the company these people call for that? Cause it sure ain't boiler, so who's the steam expert company?
You know, it's unfortunate that the other company that kind of mentored me, the owner of the company's not there anymore, and they turned to scorched air. So, I don't know,
They turned what?
scorched air,
What is
they went to
scorched
forced air stuff.
Oh, forced air.
Yeah.
Who's this?
We're on the camera,
Oh.
so.
You
Alright,
gotta tell people you're recording this stuff, man.
I
You
did.
did,
Oops.
twice.
We gotta have a flashing red light for, on the air.
Now I'm gonna quit asking questions. I'm just gonna sit here. This is a good alibi that I was here this evening in case some shit went down.
Yeah, we'll make mention when you leave. So 1.0 water fills about 28 cubic feet of pipe when it comes to steam. That equates to 48,000 cubic inches, right? It means when you fill 28 cubic feet of pipe with steam, it gives up its heat and returns to the size of that pint of water. So 28 cubic feet, when it condenses, comes back to this size. What happens inside that pipe? It creates one hell of a vacuum, and I've seen it pull water out of the boiler.
Yeah, I've seen it happen too.
Okay.
Yeah, that's pretty common actually. A lot of them have check valves. I mean,
Yeah.
out there in Chardon, we had some schools that actually had check valves up on so that wouldn't happen because the system was so large, you know?
Right.
It would pull out the boiler.
You have to have different vents for a vacuum system. You have to have them push the air out, and you have to have not allow air to come back in. Okay? I don't remember which one of the main lines it is, but you get vacuum vents, you have to specify it. Okay? That massive vacuum is useful for that right there. Back in the old days, they would use a damper system on a boiler when it was coal fired, and as the pressure built, it would close the dampers off. That thing would cook all day long and suck it into a vacuum. So it would heat the entire space all day on that fire. So that's the older systems we're talking about here, right? So, like you said a minute ago, Rick, why don't we see these systems? Primarily due to lack of understanding and the initial investment.
You know,
Right.
the world ain't getting any smarter.
Okay? if you think about what it takes to heat a building, I'll use National Acme, for example. They went belly up, and we had 100,000 square feet that we were heating on 1.5 mil and another one running in standby. They wanted to take 80,000 square feet and put radiant heaters on it that was open in the plant and then use chain link fence. It was 1 million BTU to heat that in that plant. 80,000 square feet, 8,000 square feet, because there's no walls there. So, with the vacuum pumps running on that system, we could heat that entire space with less than 5 million BTU, once the radiation got hot. Okay. A lot of studies out there tell us vacuum systems can save 50% on your fuel bill. Is that important today?
Yeah.
It was important back then, right?
Yeah, but that's like geothermal, you gotta look at your payback and whatnot.
Additional investment.
You know, that was the industrial age, okay? Now it's, you know,
Well,
fastest, cheapest, I'll do forced air, make up air unit, boom, and
a church like Pentecostal, like we're working at right now, right?
Right.
And you've got, I think that's 1.8 mil total in that building. Imagine what it takes to heat it from a cold start. The other church that we did last year, or 2 years ago, okay? If we'd had a vacuum system on that, they wouldn't have near as many problems on a startup. That building leaks so bad, it takes 2 or 3 days to warm it up, and they shut it down. Okay? So all that being said, what's the best pressure to operate a standard heating system at?
As low as you can go.
As low as you can go, right? In most cases, we're looking at 8 to 16 ounces. Okay? One of the most important lessons I learned with dealing with steam is when in doubt, lower the pressure. I got out of the Navy and I started working on steam and heating, right? What's my first thing to think? Jack the pressure on it. I had pipes shaking everywhere in the building. You know, somebody taught me, lower the pressure. That was a lesson that smacked me in the face. So, back to the zone valves and the heat exchangers. Heat exchangers, you've seen the 1/3, 2/3 valves on the heat exchangers? You got two valves, one smaller than the other?
no, never seen that.
Yeah,
What kind of heat exchanger?
any kind of heat exchanger. When you're going to steam to water, steam to whatever you're heating, the reason they do that is they can modulate them much tighter. The CV on a valve changes.
Well, I just see them sized with the orifice for that box or that coil.
Yeah.
They're not a high and low or anything like that. They're sized for that BTU with that orifice.
Well, on a shell and tube heat exchanger, okay? If we're floating that and we open a little one first, right? What's gonna happen? We talked about the steam being sucked into that piping. Well, we open a little one first, and then once it's hot, the other one starts to open too. How do we check the low water cutoffs?
Usually they have a test button.
Test button, blow them down. What's H should the boiler be in?
Firing.
Firing, why?
Because that's
Make
not
sure the
gonna
burner-
shut off if it's not running.
We wanna make sure the burner shuts off, right?
Safety controls is what's important.
Right. Okay. So, this is a couple of images that, from a recent boiler that we opened up. Okay,
What?
this thing was still working, believe it or not, when you opened the test valve. This was, we inherited this from that other company we were just talking about.
I wasn't talking about any other companies. I did not slander, persecute, or condemn in any way,
So,
anybody or anything.
when we're looking at boilers and the safety devices, what else do we look at?
Water chemistry.
Well, safety devices.
Oh.
Our safety valves, right?
Yeah, relief valves.
So whenever we go into a boiler room, we should be testing the low water cutoffs. I don't care if we were in there 10 minutes ago, I mean, a day before, you know what I'm saying? We're gonna check those low water cutoffs. Right? Lift the safety valves, just straight up and down, don't rotate the handle on it. Okay? What happens in the event that we don't test the safety valve and something happens?
Reliable.
Sorry?
We are liable.
Liable, right. We were the last ones there. Okay? So I think, we talked about superheat. What is superheat and steam?
Steam,
Temperature over
heated
boiling
above its
point.
change of state.
Sorry?
Steam, heated above its change of state.
Okay? So basically, you're adding heat to something after it changes from a liquid, right?
Steam, yep,
Okay.
change of state, additional heat added.
Now, I scabbed this off of YouTube again, and some of you may have seen it already.
A little bit of a play on words there, and that's it.
Says a meteorologist that you get cloud formation like that. What really is the steam?
A little bit of a play on words there, and that's Jeff Stevenson.
Condensing to form kind of like a cloud. Right?
Okay.
When you have condensed air molecules, you know, Chris, as a meteorologist, that you get
Sure.
cloud formation like that. What really is the steam is the invisible stuff right at the very tip of your tea kettle. That's really what steam is. By definition, steam is invisible. So we're going to see if, and you know, steam is 212 degrees, and we're going to see if this quote unquote steam is hot enough to ignite a match.
Really?
So go ahead
Okay.
and see if you can't just put it right in the path.
So I have a matchstick
Yes,
here.
and get it nice and close. It doesn't seem to be working, right?
What kind of steam is that?
And the reason for that
Saturated.
is, if you can go ahead and set that down.
So you
Is that-
set me up to fail.
I didn't set you up to fail. I set you up to learn
Just
something,
okay.
Chris. To learn something. Because
Fair enough,
this
Jeff.
is actually condensing just a lot of water,
Okay.
as you can see, and so we're actually probably moistening that match more than we are.
That's what I was thinking initially when you told me to do that.
Exactly.
All right.
So what I need your help doing is if you put those down, put on some goggles.
Okay.
We're gonna get our blow torches
Lettuce.
here.
Okay.
And we're gonna go ahead and you're gonna kind of torch these bottom three rings, and I'm gonna torch the top, and we're
Okay.
gonna see if we can't superheat this steam.
Fire it up, my friend.
All right, here we go. And now you'll see that some of the water that's collected in the bottom is gonna kind of squirt out, but that's pretty normal.
Okay.
And what we're trying to do is we're trying to get to the steam hotter and hotter beyond 212 degrees Fahrenheit because we want it superheated. And how we'll know that it's superheated is that the steam will no longer be visible. You see how it's kind of
Really?
getting clearer and clearer?
It is.
And now this is the dangerous part is because now you can't really see it. But it's actually the absolute most dangerous portion. Get right in there, Chris. Don't be shy.
I'll get after it,
I need
buddy.
you to help me here. I need you to help me. We got it superheated. All right. Now I'd say do you see it, but you can't see it.
I
Right?
don't, no.
You don't see it. So now we know that we're pretty hot. So if you want to put yours down, go ahead and turn your torch off. I'm going to continue to torch. And go ahead and try a different match, one that we haven't moistened.
Okay.
I'm going to keep it heated. Yep, and put it right up next to it. Ooh, and as you can see, we are actually able to light a match. I wanted to stay on too long, but we are able to light a match, right? You can try another one if you'd
Sure.
like. Maybe come in from the top. Yes, perfect, perfect. Maybe let's try a piece of paper. How about we try a piece of paper? Still use the tongs. And just put it right up next to the nozzle there. And as you can see, put it right in the center of the paper, right in the center of the paper. Now, it's not gonna light the paper, but it is doing that browning, right? We are actually able to burn it, and there's all this invisible steam that's superheated that is igniting our paper. Now, I did bring one more fun item.
Okay.
Okay. Now, normal paper is okay, but I brought you, if you wanna put that down, some flash paper. This is like the magician's tool, so if you wanna put that down, and I'm gonna keep heating this up because I need it to maintain that super
Okay.
hot temperature. All right, and just go ahead and just put it right in the tip there. Now, this is a magician's flash paper. All right, and it just immediately kind of goes away. Isn't that nifty? Do you want to do it again? I know you do, Chris.
Please.
All right, we're gonna use like twice the size of paper though.
All right. Still
Okay, so let me
superheated?
make sure it's superheated. All right, are you ready? In 3, 2, 1, put it in. Woo! And it's such cool paper because it's gone before it even hits the table. Isn't that amazing?
Find that somewhere in thin air.
Yeah,
That's
yeah,
cool.
it's out there, it's
That's
out there.
science.
Yeah.
Now, did you ever think you'd see something start on fire by steam? Okay? Well, the next one is, how much water expansion or steam expansion is there when we boil water? If we take and we heat a gallon of water and it instantly flashes, what happens?
Can cause many things
Sorry?
to go
It's
off.
like 17,000 times the space.
But how about a water tube
1700.
bursting right through your house? To mimic a real-life situation, the roof of the house has been constructed to California Building Code specifications. And the water heater contains no explosives. They turn on the power, hunker down, and wait.
Field ready? Everyone's in position? Cameras are all rolling?
Yeah, we've got a nice little red house out there sitting on, you know, like everything's rosy.
Rosy on the outside, but roasting on the inside.
Okay, everybody, we're at 300 PSI. That's twice the tank rating. Keep your eyes peeled because it'll go any minute now.
As the pressure inside the tank mounts, so does Jamie and Adam's heart rate.
315 PSI.
Oh, this is killing me.
320.
Any second.
325.
This is excruciating. This kind of stress on a regular basis can't be good.
No, shortening our lifespan.
We're gonna make it 350.
Suddenly, the heater launches and tears through the roof like it's tissue. You could practically have a 3-course meal while you're waiting for it to come back down.
Look at the house. What house? I don't see a house.
So, did that water heater explode?
Yeah, the bottom blew out of it when we watched it.
The bottom blew out of it, right?
There's-
Yeah.
It became more of a rocket though, right?
Yeah,
It's
to
directional.
expand out the week it blew out, they're designed to blow up
Yes.
instead of out sideways and kill people, they're
Right.
straight up.
Right,
Did they do 2 videos of this same type?
yeah.
Because the one went right through the roof. This one here, the whole thing went out.
So I got a question about this chart.
Sure.
Why would a manufacturing facility run something at 30 PSI, have 274 degrees temperature, have the latent heat at 929, which they could get that in a vacuum at minus 15 or negative 15 or whatever. Why do they need the 274 degrees? Why do they need the sensible heat? In a vacuum, we can evaporate, the BTUs are there, but are these I would like to think they're the same BTUs, but why do we
Are you talking
cook?
about the latent heat?
Yeah, we don't cook in a vacuum at home, so for heating, technically the chart says the BTUs are the same, but why does the world use a positive steam pressure then?
It's more about how the system is designed with different valves on it. Okay. So, we talked about that job, that North American boiler, right?
If we wanted to change the temperature of our product, we change the temperature of the steam.
Not necessarily.
Yeah, that's
What's
regulated, but look at the
what-
vents valves.
What's latent heat?
Well, that's the hidden heat that does the work that you can't physically touch or
Right.
see.
So, we're looking at sensible temperature though, right? When we're changing the temperature of a process.
Is that why then? That's why a Spence valve is gonna be a positive pressure, and the pressure corresponds to my temperature chart for the temperature I'm trying to achieve out of that vessel.
Yeah.
So, again, where do we use a system in the negative inches to obtain these latent heat BTUs? Where can we use those? For heating only?
We use it in heating, we've seen it in process too. Look how much heat you're giving up. Now, are you gonna get it hotter than 161? No. But you're coughing up 1,002 BTUs at 161 degrees. So the higher the pressure goes, the higher the temperature goes, right?
Yes.
So what we're looking at here is 5 ounces, 227 degrees.
Yeah?
So it's not so much the latent heat, it's the temperature of the steam at that point. You know, in this one, what's the highest one that?
So why don't we heat with a positive? Why would we heat with a negative? other than the BTU, I mean, if we're removing BTUs, I get that, air conditioning, but these latent BTUs,
What happens to the latent BTUs? Look, it's going down. Until we superheat it. Until we get up in the 1,200 pound range, and then we're back to 1261.
well, it's gonna go positive as soon as you get over 0
Right.
PSI. Doesn't have to go to 1285 before it's useful. It's,
Well, I think we might be looking at latent heat versus temperature here.
I am, I'm trying to
Okay.
figure out why we need
So
the
what's-
temperature and why we just don't do life with latent heat. You know what I mean?
It depends on the process, what temperature you're trying to maintain. I mean, some of the fabricating plants that I worked at for foil and, vinyl, they wanted 400 degrees. Okay?
So if we got a Spence valve and we're trying to heat up some domestic water and we got a heat exchanger there with a Spence valve on it, and we got these BTUs and the BTUs are better in a vacuum, why wouldn't we just use the vacuum? Why would we actually put a physical sensible temperature to it?
You could. Why people don't use it is, again, the lack of understanding and the initial cost of the vacuum pump.
We don't need sensible heat to boil water, you can do it with latent heat. So why would we even go into, if I wanna make 227 degree water, I'd have 5 PSI.
Well, what's it take to get us to this 970 where it boils at 212?
It's still all the BTUs gotta be put in there.
We're not talking total heat here though. If we're bringing the water temperature from 112 degrees to 212, how many BTUs did we spend?
Did we spend?
Yeah.
Well, it says 970 BTUs latent heat.
We're
To
still,
get to
we're still at
212.
water here. So if we come from 112 degrees to 212 degrees water, we spent, how much, what's the BTU?
What is it, one pound for?
It's 1
what is
degree.
that? One,
Yeah.
what?
1 gallon for one.
What's
One
that?
pound.
One pound, or 1 degree for 1 gallon of water basically per hour.
Is BTUs, we should all know this.
Yeah.
Somebody
One
has-
pound,
You're spending a BTU
1
degree here.
in 1
From
hour.
112 degrees to 212 degree water. When we're here at water and we're going to steam, we spend that.
Oh, that last degree is, okay.
Yeah. So you have sensible heat that comes in at total heat, which I don't remember is on.
But I
this chart.
still have to make the steam to condense it to get into the vacuum, unless you're using vacuum pumps. Right? You gotta make the steam, condense it, and then apply it to the process.
Yes. So what they do in plants like Acme, when it was around, is they would use, they had a steam engine that they drove all their processes on, belt drives, all that stuff. They'd use a low pressure, would feed to the heating mechanism, and that would go through the vacuum system.
Sometimes we need the pressure on the system to raise the boiling point of the water. That's why we use
Yes.
radiator caps on cars, because if we didn't, our temperature gauges on our cars are rated at 240 degrees. We're down at 220, we're already over the boiling point.
Sure.
So on cars, we use them for the opposite reason, because we need to raise the boiling point of the water.
Right.
So that's the reason why the temperature and pressures are so important. That relationship is important.
Exactly.
Depends on what you have to get out of it.
Depends, again, we're here talking about heating tonight, right? But different processes require different temperatures, which require different pressures in the system. Okay?
So you're saying a lot of that is engineered into the system, has to be in the process, there's a lot more engineering involved than just temperature and pressures to make it work right.
You have to understand what you're dealing with, yes.
Well, it's the art. So an application that's in my mind is they need 125 pounds of steam available because they're moving product with it. They're pushing product with it. So they're already on the positive side of life for that. There's nothing for a vacuum there. Until they condense it and apply it to an application to put a specific part of that in a vacuum. Because, if we want to control a cooker, we're going to control the pressure. Hence the springs and the Spence valves and what
Sure.
operating range we're at,
Right.
I'm just trying to figure out why the whole world doesn't work on vacuum. If the sensible heat is lower, or
Nature
probably
abhors,
expense.
nature abhors a vacuum, that's why.
Do what?
Nature abhors a vacuum.
Abhors?
Hates a vacuum. But think about a pressure cooker. What happens if we pressure
Oh yeah,
cook
that's how we
something?
cook these bottles down there, but
And then it creates, and once it's sealed off and recondenses, what happens? It's hard to get the lid off sometimes, right? Unless you vent it. but you still have heat available.
Well, I think the temperature is a big part of this because we dried the product in a vacuum, so we didn't go over 220 degrees, but we still had to dry it out, so we put it in a vacuum. The jackets were still 200. The other shit that we wanted to cook, you know, we run 60 pounds over there and heated it up and cooked the product with, I guess, sensible heat. Over here, we're removing latent heat in a vacuum. Is that right? We're removing it.
Removing latent heat,
Are we removing it? What are we doing in the vacuum?
you're reducing the boiling temperature.
Alright, so that's
We're
it there.
talking
That
today-
changes everything there,
Yeah.
so, you know,
Yeah.
you're in a vacuum, so it's all.
So if you're doing a
Yeah.
process, like you said, you're heating X, Y, Z, and you want.
I can dry it out, Tom, but can I cook it? If I put a piece of chicken in a mason jar, hooked up the vacuum pump, you know how they remove the moisture and all that, and I'm gonna move all that out of there, I'm removing
Yeah.
heat, I'm removing BTU out of there, but am I gonna cook it? Why don't,
It
Probably
depends
not.
how deep your
Right.
vacuum.
you see what I'm saying, am I gonna cook it?
161 degrees isn't gonna cook it.
Yeah, so
You
you already
need
have
to-
to have that steam up there. If you
Cook.
hold down to 20 inches in a vacuum chamber, it's gonna be cold.
Right.
Right.
Right. So
So-
you do need the steam in there. The vacuum is there for the outlet side, I guess.
For the processing, different process of it to dry it out.
Right.
And once you drop that temperature, that heat's, you're still 200 degrees in the product. So as it cools down, it's gonna pull that moisture out over to dehydrate.
How are we gonna heat a building in a vacuum? I need temperature,
Well,
I need
that's-
specific heat,
That's, okay.
sensible heat rather,
I understand what
cause
you're
I
saying.
can't, I
is
can't
that
cook a piece of chicken in a vacuum.
You've got traps, right?
Yeah.
So you're pulling everything from the trap through the system. You get steam at the traps close.
Yep, I like a vacuum for that, that's great,
Yep.
blow that steam through.
Yep.
Steam's what's giving up the latent heat into the radiator and all that
So we
stuff.
get it to the trap, now our condensate return system is in a vacuum of typically 8 inches of mercury.
Yeah, that's all fine, but we're looking at BTUs in a vacuum as a heating application.
Right,
No, we're looking at it as how many we can pull through the system.
so let's
That's
forget,
all,
let's
Jay.
forget about the pump for a minute. Remember we talked about the old fashioned boilers with the dampers on them?
Uh-huh.
Okay, you heat that system up, you had, loop seals at the end, there were no traps on them, like a one pipe, okay? And you simmer that thing at 160 degrees all day long in a vacuum. And when you condense, what's gonna happen, it's a natural flow.
So how am I gonna heat this warehouse you were talking about if my system's in a vacuum? I still have to
Well,
make
your
the
steam
steam.
system is not in the vacuum.
Okay,
Okay.
okay. So
That's-
then we can't say that a steam system will work better on a vacuum because of the BTUs that you get out of it. It's not, it's removal. Removal.
Depending on the system you're looking at, okay? If you have traps in it, your condensate side is in the vacuum, but you're removing it. Every time that trap opens, you're sucking that air through there and the steam through there, back to that trap.
Alright, so I can see that we can get as much heat in a vacuum, but the vacuum isn't generating the heat.
Right.
That's how I took it when we're comparing BTUs. So
Right,
we
but-
should run all of our boilers in a vacuum because we can get more heat out of them.
In
No,
a
we
nat-
can't.
in a natural system with no traps or whatnot, you could heat the building at like that, at 161 degrees.
No, I could.
Why
I
not?
couldn't do that, cause I couldn't cook a piece of chicken that way. And I sure ain't gonna do it in Cleveland, Ohio, because we got temperature differences here.
What happens?
What I want is not what I heat
So
at, I
let's-
heat above.
Let's look at these boilers that we were talking about, the old fashioned ones with the dampers.
Yeah.
They're all chain driven, and it's operated on a pressure control that is like a bellows, okay? As the pressure built on that, it would start to close the doors. Pressure built to whatever.
To control the fire,
Right,
right? Yeah.
okay? So now, the boiler would simmer down to there. As things started cooling off, what happens to the pressure?
Those would go into a vacuum,
Right,
because there's space, the condensate is removed, and what's left is the vacuum.
yes.
But that vacuum's not heating, the steam that went in
The
was
steam
heating.
is still heating, because I'm still boiling water.
Yes.
At 161 degrees.
I understand that fully, I just didn't understand how, if
Yeah.
our entire system was running on a vacuum, because you talked about what's the lowest amount of steam we should have, and it's the most we can get the work done, so we should run every boiler in a vacuum. But no, your return side, yes, all your, some process, yes, if you're drying stuff out,
Well, we're talking about heat now, we're not talking about a process system. This is specifically a heating discussion. okay? I understand what you're saying.
So you're saying, so are we safe in saying that the vacuum is all on the condensate trap side and that half of the system?
In today's system.
We're not making a system that's vacuum and putting vacuum to something and trying to make it heat. It's after the fact, after the condensate traps, pulling stuff back
In today's
through.
system, yes, with our natural gas valves or oil burners. Okay. The old boilers, the coal-fired boilers would work wonderfully well like that.
So if I want more heat, sensible heat, on this chart, I need to increase the pressure.
To what?
Well, to
For-
the
for
least
heating.
amount that I
For-
need
for
to
heating.
complete my process.
We're not talking about process.
Well, process as the building heat, the system,
How much heat do we need? to
as
heat
little
the
as
building?
possible.
How much heat do we need? I
When-
mean,
To the
212
complaint
degrees
of
is
the
radiator.
coldest person, the complaint of the coldest person is what we want, okay? So, but we wanna keep it to the minimum, I agree, ounces. You know, I like the steam radiating, I don't like it
Yeah.
trying to push condensate back.
Yeah, and
I'm
really,
just
we
trying to
should,
apply the vacuum to this and looking at it as the whole thing, the whole building is in a vacuum.
if you start a system that has traps in it, and you come in and the boiler says, okay, it's time to start. Vacuum pump starts, and we already have a vacuum on that system as it's starting to pull down, okay? The boiler's running, we start building steam, the steam's gonna jet through the piping, start hitting the traps are gonna start to close, our vacuum's gonna get deeper, okay? What's the pressure on that steam side? We don't know. Is it 5 pounds? No. All right,
I think the point that I missed was the 212 degrees at 0.
Right, and
Yeah,
atmospheric,
okay.
atmospheric pressure, I guess that.
We
it's
have
atmospheric
that,
pressure.
we have to have that, we are making some steam.
Correct.
But when you said that I interpreted it as we could make this temperature steam, that in those vacuums,
mm-hmm,
we're not making that steam in that vacuum. We're not making those BTUs in that vacuum.
well, actually, we could in the old style boilers, not with what we have today.
If it was still generating steam.
Yeah.
Just that somewhere there's
It's
a break
already
in the
already hot,
system
okay.
to where we're on the return side now, wherever it is, in the radiator, in the steam trap or whatnot, that throws it into the
In
vacuum.
today's systems, yes, yes. Okay, and there is a place for it in the process side too, for a lot of different things.
For heating or for the removal of the air and the condensate to get
Yes.
our heat where we want it?
Yeah.
Okay.
Imagine a 100,000 square foot building and you had, what I'm thinking of had 5 million BTU boilers on it that they would cycle every year for heat. They didn't need it. We ran them on one boiler with one standby. Okay? They had all the vacuum pumps working. I think there were 7 of them if I remember right. And the only thing that kept me from going higher or lower than, I think it was 5 pounds on that steam side, was that they wouldn't allow me to change a pressure regulator for a steam to hot water converter in the building.
Yes, if you have all that vacuum, you don't need, other than what the chart says for that temperature, for that particular radiator or whatever's going on, that heat exchanger.
Right.
Nothing extra, you don't need it, especially if you have the vacuum.
Yep.
The extra is the mass to push it through, to make up for some other, air, condensate traps being bad, flooded, condensed.
Okay. More often than not, if it, in a well-designed system, we're not pushing condensate. It should be naturally flowing,
Yeah,
okay?
but this is Cleveland with worn out buildings and
Right.
steam houses that are buildings that people trap the whole building,
So,
but I get it.
back to this for a minute. What happened with this? Who can explain it?
When, I remember when I was a kid, we used to have those plastic rockets. You fill them up half full of water, then you pump the air up and the crap. That's basically what you did with a hot water tank.
Mm-hmm.
You had it built so much pressure that the water started actually boiling and made an air pocket, which made it expand, had nowhere to expand until it blew, and then it took off like a rocket, because that's actually what it did. It became propulsion.
Right, there's no steam in that tank until when?
When it flashes the steam at the 212 degrees.
Pressure
They
drop.
float it dry.
No,
Pressure drop.
pressure drop. Because as you build your pressure, you're still at equilibrium on a boiling point. Okay? That thing popped at 320 pounds. What's 320 pounds on that?
It's pretty hot.
I don't think
Probably
it's
140 something. 310 is, well, that's Celsius.
What's the highest one?
250 is 406.
So you're over 400 pounds.
Yeah.
okay?
So you're saying there's no steam in there till you get a pressure drop?
Until the
bottom
tank
comes
blows.
out,
Why is there
instantly,
not steam in there at 212 degrees?
Because it's a
There's no
liquid.
room to expand.
Oh, it's still there, it's compressing the water and it's taking up space.
because your boiling temperature and your pressure are corresponding at that point. So if you're at, use this term, what's the bottom one, 250?
Correct.
So if you're at 250 pounds, right?
Yeah.
406 degrees, and the bottom pops out, now what do you have? You're back to atmospheric pressure. Everything flashes
Off pressure.
instantly.
So you're trying to say it flashed off?
Yes,
Right.
it's still water until
I
that
don't
bottom
know, I
pops.
think it's the resistive pressure of those welds when that thing relieved. You know, all that pressure was there, the pressure just didn't come about when it flashed the steam, the pressure is what blew the bottom of the tank out.
No, we're not talking about pressure. We said, when did it become steam?
Oh,
Yeah.
okay, when it went to atmosphere.
Right, when we went from 250
There was
pounds.
no room for it to be steam, that's why it imploded and blew the bottom out.
We still had,
Right.
that water was building pressure, right?
Yes,
Okay, as soon as that thing blew the bottom of it out, now we saw the pressure drop and we went from whatever, I think it was 3 1/4.
Right.
To 0 or atmospheric pressure, everything's steam. That's why it's so dangerous.
so it's flash in space is
Correct.
what you're
Yeah.
trying to say.
Right.
When it flashed off, straight to atmosphere when the bottom blew out.
That's it.
That gave it the propellant to just keep going,
And 500 some,
First.
they say it went up 500 plus feet.
going off.
So steam is very useful, it can be dangerous too. So I meant to ask this in the beginning, when was the first boiler used? Built?
I'm gonna say before Christ.
That's probably right next to the Egyptians' carpet in the window with the water on it when the air was going across it. Probably like right next to it or something. Economizer boiler. It was hot. Somebody was heating up.
No clue.
Mike? Right around Christ's time, you're right. 10 AD.
What did they use it for?
Hero made it, it's called, I can't pronounce it, I'll show you a video in a minute. Iliopile, I think, right? And basically it's a turbine, you put a flame underneath it, and at some point he used it to open and close doors.
You know, I think I've seen that.
Yeah.
Because there was, in the 1800s, one of these inventors that was doing some trickery shit with that process, moving doors.
Yeah.
I can't think of what he was selling.
I'll show you a
He
little
invented
video.
something, but the whole process was false. He was using that. He wasn't using electricity for this. He was using that steam process
Right.
to move stuff versus electricity or something.
It's really cool if you think about it. Steam is a wonderful device. Steam cars, steam motorcycles, you know?
If you can recover the water, I mean, yeah, you've got, I still think it's more efficient than some things we have today.
Yeah.
Depends on your fuel and all that, I get it, but, I mean, it recycles. Doesn't leave the atmosphere as carbon monoxide or dioxide, it recycles
Sure.
the water. So if you did, like, you know, hydromatic power and stuff like that, waterfalls, you know,
Right.
hydronic.
So back to the water thing for a minute, water going to steam. If this container could be put to 300 and some degrees, or 300 and some pounds, at however many degrees, 400 plus degrees, and it burst, what's it gonna do? How much is it going to expand?
Well, anytime that flashes to steam, it's the 17, you're saying 1,700 times the space. I thought it was 17,000 times the space.
Right, this
But
is
you-
roughly 28 cubic feet.
This is why you're not allowed to have liquids in steel mills where they have molten lava,
Yeah.
right? Because that shit falls in there.
It's like throwing water on a hot skillet. Right? What happens? Instantly vaporizes. Who of us haven't been burned when we throw oil in it to cook something and then throw water, something wet in there? Right?
Something frozen that has ice on it, when it goes from ice to vapor instantly.
Let's see, our industry's safety hazard is filling the hot water tank if it's hot, the vessel if it's hot. You know, we're not gonna see that unless somebody put a concentrated amount of heat on something,
Well,
right?
down the road here on Sprague Road,
Or they run it dry.
4 or 5 years ago, there was a water heater that they say exploded and killed a guy. Okay? If you drive past the house back then, you never thought to get pictures. Water heater came up, next to the chimney, and you could see the roof splayed out like that. And when it came back down 20, 30 feet away, it went into the living room and the roof was pushed in.
So what caused the failure of the hot water tank?
Safeties didn't work, relief valve plugged, burner kept on, I don't know. Could have been electrical too. These are electric tanks that they're using. So that they say it exploded, I don't think so, I think it went up. Just by looking at the roof,
Went up, meaning what?
like this one did.
Well, they're designed to blow out that way.
Well, what I mean is this thing went through the roof. It didn't explode like everybody thinks it does.
No, the bottom blew out.
Yeah.
That's your rupture disc, that's your failure is the
Right.
bottom, so they go up instead of
Look at the house. What house? I don't see a house. I don't know what you're talking about.
This actually surprised me. The house was no hindrance whatsoever to the rocket. It probably would have gone through several houses like this before it stopped going.
It's like a fairy tale come true. The water heater puffed, it puffed, and it blew the house down.
It just goes to show you, you know, there's danger everywhere.
Man.
Did you know what was lurking in your basement?
The guys inspect what's left of their once charming home.
The bottom of the tank went from concave to convex, probably in a split second. There's a hole in the roof. It had to go through 2 layers of 2x4 trusses in order to make that hole, and yet it totally did. And it did it without breaking any of the 3 windows in here. That's a rocket, my friend.
Yeah.
Not a bomb.
Where did we see a tank that looked like that recently? I think you guys were there.
Didn't we see an expansion tank that looked like that?
Yeah,
I know what you're talking about.
it was Franklin.
Yep.
Yeah. So,
Where's the ceiling put in?
Did we leave it in the ceiling?
We never took it out, yeah.
steam is fun.
Did you guys put that in?
Oh, we did leave that up there.
I think I left
It was that long,
down.
narrow one. That thing was probably sized incorrectly and everything. Wasn't it a narrow one?
It was long.
Was it 6 inches?
You guys
wide?
did Franklin?
I did, yeah.
Was it
Yeah.
compression tank?
How was it? Was it everything I thought it would be?
We can't speak derogatory about anything, Kevin, so it was an excellent experience. I grew as a person internally, and, you know, it's a win-win for everybody.
And it works.
Well, I'm glad.
Well,
far.
that heat timer. Correctly, there's a lot going on with that heat timer.
You mean the antiquated thing on the wall?
That's all gone. I ripped that whole wall off.
Okay.
I unwired all, that's all gone.
Yeah.
There's just a heat timer there and 2 switches and a couple transformers going out to who knows where.
Are we still doing outdoor air?
Oh yeah,
Outdoor
yeah, I
reset?
got that heat timer staging the pumps, or the primary, secondary pump, no, I'm sorry, primary pump, high and low fire, outside air, reset.
What's the heat timer doing? What do you mean by heat timer? Like
The
minimum
brand
runtime?
is heat timer, it's the brand,
It's a
Outdoor
reset
reset.
control.
it's outside reset,
Oh, okay.
you know, temperature drops, boiler goes up, but it's also bringing on the primary pump and the first and second stage of that boiler. There's 2 fire on that.
So how does it bring the primary pump on? Is it just by outdoor temperature, so when it goes on a?
Yes,
Okay.
separate entity, only as an output. There's a relay added that you could bypass to turn that pump on. That's all it's doing, and the primary pump's the building pump. Outside air comes on. Secondary pump is on relay 2, and that's,
Say
actually,
outside
no,
air?
what's that?
You say
Combustion.
outside air?
Combustion.
Outside air.
Oh, we
Outside
put a
air.
combustion fan in there?
No,
No.
outside air temperature.
Oh,
It's on the building pump.
ambient, and outdoor
The
ambient.
loop temperature, that brings that on. The controller stages first and second stage off of relay 2 and 3 internally, according to the chart of what we want per degree of drop, which that's what I was talking about can be adjusted, because it's probably high fire with no load, and it needs to have some differential in there. Yeah, so it's really a nice heat timer. I like it. I didn't like it at first, but once I got into it, I really like it. It's very simple. I just told Myron we need to put one on over here at
the other job.
customer, yeah.
Yeah. So this is what the Elio pile. I don't know why there's such a delay on this.
That's a lot more efficient than, what's that blue one?
Techmar?
Yeah, them things are big money, and even the Johnson Control.
So, like alcohol, maybe there?
Yeah,
For the burn.
Oh yeah, it's like an alcohol stove.
That makes some hot air.
So this happened to be the emblem of my rate in the Navy,
Which was,
DT,
what was it?
boiler.
Make Master Chief?
I was lucky to make third class place.
I just couldn't get over calling myself a seaman. I sure couldn't say Seaman Siler coming, sir.
I would
Sure
never
wasn't
let
gonna happen.
So, he's heating the water in here, what's gonna happen? The thing's gonna start spinning.
Yeah, gotta go somewhere.
Got the little nozzles on it.
Run and drill with that.
Well, unfortunately, after about 70 AD, just died off, the whole steam concept until sometime in the 700s, when people rediscovered it. And imagine what the Industrial Revolution.
Hey there,
would've been like.
it's James once again, and I have a very interesting motor to show you, which is called the Hero motor. It was first described in 1 AD by the hero of Alexandria. And the neat thing about this motor is that it was just used as a toy. And it had no practical purpose until 1500 years later, when somebody realized that this motor can input mechanical motion and drive a system. So the point to take from this is that sometimes you might have invented something that is really important and you might not even know it yet. Now obviously these motors are not very powerful and they're more of a showcase item. And there's a few tricks you have to know with these things. The first being that they don't really typically run on a candle flame. You have to use some sort of alcohol solution with cotton swabs dipped in the alcohol, and this allows the flame to burn at a really high temperature and heat the water in a rapid progression, thus allowing the steam to escape at a sufficient velocity, which allows the mechanism to rotate. Other than that, I filled the sphere about a third way up, and that seems to work as well. But other than that, I'd like to know what you guys think about all this. So please leave a comment, like the video if you enjoyed it, and also make sure to
I think
subscribe.
there should be a backyard competition for that, where companies can just build their own steam engine out of their own shops. And,
See what you power do.
See you on the news.
I'm surprised, Tom, you don't collect steam whistles from the ages?
I collected way too much stuff for a long time.
Oh, these are funny.
What's a putt-putt boat? Does anybody know?
It's a candle in a boat.
Have you ever seen these? Do you know how it works?
Never seen one.
Except the putt-putt boat. So this is a putt-putt boat made.
Let's think about it before we watch the video.
Except the putt-putt boat.
So it's got two tubes on the back, right? And you're heating a little tiny chamber. You fill it with water originally.
A shaving can. You can see that in the middle of the boat here, we have 2 copper pipes going up into a sealed flat chamber. In order to start the boat, what I do is I fill the 2 copper tubes with water. Then I have a little candle on a spoon here. We just light the candle, and I stick it in the boat. And there it goes. The way this works is pretty interesting and pretty counterintuitive. So this will keep running as long as I have some fuel in that candle there. It won't ever actually run out of...
So why does it do that?
What's clicking? Is there a propeller on there or something, or is it just steam?
It's
It's
steam
all
blowing
steam
up,
on
popping
it,
it,
but
and
how
that's
does it
propulsion.
get water back in?
The vacuum after the steam goes
Exactly.
out sucks it back in.
Exactly. It's pushing it out one tube, sucking it in the other, right?
there. It won't ever actually run out of water.
The water stays the same in the chamber no matter how long it's been. The way this works is pretty interesting and pretty counterintuitive. So this will keep running as long as I have some fuel in that candle there. It won't ever actually run out of water. The water stays the same in the chamber no matter how long it's been running. So you'll notice coming out of the back of it, it's only water coming out the back. There's not actually steam or bubbles coming out of the back. You can see in the slow motion footage of the boat passing over that it is indeed just water shooting out of the back. But if water's continually shooting out of the back, how does it not run out of water? When you stick the candle under the boiler, it causes some of the water to evaporate in there. And that evaporated water expands because of the heat and because vapor takes up more space than liquid water. And so it pushes some of the water out the ends of the boat. But then when it expands too much, it condenses back into liquid water again. And that takes up less volume than the vapor, and so it actually creates a small vacuum in there, and so it sucks water back in. So it's a continual process of shooting water out and then sucking it back in, shooting it out and sucking it back in. But here's where it gets interesting. How could something, if it's continually sucking in and blowing out the exact same amount of water, why does it only move forward? Wouldn't it just vibrate and jiggle back and forth? One of the answers to this has to do with the previous video I made, where I showed that using certain frequencies you can blow out candles. In this shot here, I showed when you use this frequency, it blows out the candle, so there's air continually moving away from the phone enough to blow out a candle. But how can that be? Because the speaker cone's just vibrating back and forth, so it pushes air out and then sucks it back in, and pushes it out and sucks it back in. Well, the reason it can do this is because when the air is getting blown out, it had just gone through a small tube opening. And so it's collimated air, meaning that it's one column of air going through and it's not spread out. And so it has more velocity to it, and it can blow out the candle easier. And that's the same case with the putt-putt boat here. When the water's coming out of the putt-putt boat, it's coming out of the exhaust tubes from that small opening, and so it has a higher velocity. But when it's getting sucked back into the exhaust tubes, the water's coming from all directions, not just one straight line in the middle. And so the velocity and hence the momentum is coming from all different directions instead of just straight on like when it's shot out. But that's not actually the whole answer. That makes the boat more efficient, but that's not actually what makes it move forward. Because if you do a momentum balance on only one of the tubes here, you'll notice that there's always the same amount of water moving out and then going back in, moving out and going back in. So that seems like the boat should just shake back and forth. It actually has to do with what's happening with the momentum of the water in the putt-putt boat. So when the water is leaving the putt-putt boat, the momentum of the water is taken away. It gets shot out the back, and so it leaves the system. But when the water is entering the putt-putt boat, it goes into the tube, but then it hits the boat. So the water going in ends up hitting the boat. To see what I mean a little better, let's explain it like this. Let's say you're standing on the boat and you have a big ball filled with water. If you throw that big ball of water out the back, you're going to get pushed forward. So that's the equivalent of why you move forward when water gets pushed out the back. The boat moves forward. But what about when water's getting sucked in? Well, that's the equivalent of you're standing in the boat and you have a rope connected to a ball of water floating in the water. Now you can tug on that ball and that will pull your boat towards the ball, and it'll pull the ball towards you, and eventually they're going to hit each other and they're going to cancel out each other's momentum. So in the case where you throw the ball of water out the back, the momentums don't cancel out, but in the case where you suck water in or pull a ball towards you, eventually they cancel out each other's momentum. So that's why the only momentum that moves you forward is when the water's getting shot out, not when it's getting sucked back in. So that would mean, for example, if I filled this boat with a vacuum and then opened it underwater and let water shoot into it, the boat wouldn't shoot backwards like this, but it would stay mostly still. Whereas if I pressurized this with water and shot water out the end, that would still shoot it forward. Now, before we continue our experiment and explain the putt-putt boat a little more, I'd like to thank the sponsor for this video, BetterHelp. In 2022, I'm setting a new mental health goal where I want to meditate every day.
I don't want to hear anymore.
I seen that's where that shit was going.
So, Mike, when you call me tomorrow, I'm gonna tell you I can't work on meditating.
Putt-putt boat. Have we ever seen that in a heating system? The same actions?
Something about water heating or something?
No, not quite.
I think you don't you get a little bit out on a pulse boiler? Don't you get a little
I'm talking about steam systems now.
Oh, Steve.
Yeah. You ever pull a vent off a radiator, for example?
Pull a what?
A vent, and it pants? Like that?
No, I try to keep them on the radiator. I really just took one off because, but yeah, it's a vacuum.
Well, that's what's going on, right? If a radiator's not heating, you pull a vent off of it, on the radiators that have vents, and you can hear, I actually, back when I smoked, I put a cigarette up to it and it would puff, suck and puff my cigarette, okay? It's the same principle here. I got steam on one side and then I got water. I got steam and I got water. It was pushing itself back and forth. Weird stuff. Weird stuff. You're looking at me quizzically, Rick.
Yeah, because that would mean that that was the process you talked about earlier where the steam blew out versus the ratio of the steam coming in, put it in a vacuum. Steam came in, pushed it back out, steam back and forth. We just talked about that earlier.
There was a condensate problem.
You know,
In that case.
if it's in the relationship to the steam coming out versus the size of that, or if it's on that vent, yeah, blows it out, puts it in the negative, till more steam can make it up, pushes it out the hole.
Well, it depends on what's on, if you got one pipe or two pipe, okay? So if it's a two pipe and you got water panting back and forth, let's say, or a one pipe and you got that panting, that means you got water trapped someplace. All right? So, thanks for coming up and doing this tonight. I didn't know it for years, but I had steam in my jeans. I had great uncles that were steam engineers. I had another uncle that worked with Rick over on a nuclear power development on the submarines, as well as the power generation like the new plants you see around here. Also discovered that I had a great-great-grandfather that started the Canadian Pacific Railway. And that and a couple of bucks gets me a lousy cup of coffee, but it's still been in my genes, I guess, for a long time. Boiler school, 4 years on duty on a ship, RSES boiler school. A guy named Dan Holohan was a huge mentor of mine. This Lost Art of Steam Heating. Guys, you don't want to be without that book if you're going to work on steam. We call it the guys the dead men from 100 years ago. They knew what they were doing. Why did they do it, and why did we change what they did without knowing why they did it? Things like that. A guy named Tony Connor. Last I heard, Tony Connor's working on the oil wells on Alberta. Brad White, who was supposed to be here tonight, he's one of the brightest guys I've ever met as far as engineering goes. He's been working on the airport project in Boston for many years now. Steve Wheels, I think you guys have talked to him. He's helped us out on different boiler situations. Mark Etherton, which we talked to here, rating panel, and Dante DeVille, who was the rep for Wal McLean. These guys influenced my life a lot over the years. And there's others I'm sure that have slipped my mind. What I've learned though is it's really important to be part of a community that discusses this stuff and bounces things off each other. And the wall on heatinghelp.com is still there. It's not what it was 25 years ago. Area 51 HVAC was born in 1998 for sharing of HVAC information and knowledge, helping us grow. It's really important. That's how our chapter got to be named Area 51 HVAC. So I appreciate it, guys. Thanks for taking the time. Any questions? Okay.
Thank you, Tom.
Thank you.
We got a hat for you, Tom.